at Australian National University and a PhD from the University of New South Wales. Prior to her current position, she was an Alexander von Humboldt postdoctoral fellow at the Max Planck Institute for Meteorology in Hamburg. Her research interests include using large ensemble simulations to study drivers of climate variability, and have included leading the coordination and publication of the Max Planck Institute Grand Ensemble. Her talk title today is Using Large Ensembles to Investigate ENSO Teleconnections and Future Projections. So Nicola, feel free to share your screen and take it away.
Okay, thanks. And thanks for inviting me to speak today. Can you see my screen?
That's good.
Okay, great. Okay, so today I'm going to talk about using large ensembles to investigate ENSO. And specifically, I'm going to talk a little bit about ENSO teleconnections over North America and ENSO projections in the future, or projections of ENSO itself. And I'd like to acknowledge the list of co-authors on my first slide who have been instrumental in all of the work that I'm presenting today. Okay, so the first slide here shows a large ensemble, or a single model initial condition large ensemble, or otherwise known these days as a SMILE. And here you can see many ensemble members for global mean surface temperature, shown in the blue, and one single ensemble member shown in black. And SMILES are a really useful tool, as many of you might already know, to investigate the climate. And I'd just like to point out a few details of kind of the cool things we can do with these large ensembles. You can see here that we can investigate the variability of the Earth system. So we have this envelope of blue that shows us kind of the internal variability of global mean surface temperature. And one of the really cool things we can do with SMILES is we can look at the internal variability at different time points. So now we can really investigate the time evolution of the variability itself. Another cool thing we can do is we can average across the ensemble and get the ensemble mean, which is a really good estimate of the forced response to external, kind of the response of the climate to external forcing. And here you would see, if you did average across the ensemble, you can see that the end of the time series would be warmer than the beginning of the time series, which would be climate change or global warming. But also you would see around 1991, this drop in global mean surface temperature that we can attribute to Pinatubo. The other really cool thing about SMILES is that if we look across all of those ensemble members, we have lots and lots and lots of events of highly variable processes like ENSO, or long time scale processes like decadal variability that we can composite across and really start to get statistically significant differences by really having enough events to look at. And so today I'm going to use those SMILES to answer two different questions. I'm first going to look at whether Pacific decadal variability modulates ENSO, or El Nino Southern Oscillation teleconnections over North America. And second, I'm going to look at whether ENSO itself changes in the future. And so we're going to start with question one and look at the teleconnections over North America. Okay. So today when I talk about Pacific decadal variability, I'm going to use the Pacific Decadal Oscillation, or the PDO. And you can see the PDO shown on the left. You can see its warm and its cool phase. And you can see that it has this kind of characteristic horseshoe pattern in the North Pacific. It has some kind of tropical Pacific variability that looks a little bit like ENSO. And if you look on the bottom left, you can see the PDO index. And you can see how the PDO changes over time. And today I'll note when I talk about the PDO, I've actually low pass filtered this index using a 13-year filter to really tease out the decadal part of the variability. On the right, you can see a figure that talks about the mechanisms behind the Pacific decadal oscillation. And you can see that it's forced by wind forcing and atmospheric forcing, as well as ocean reemergence. And there is a component that is related to ENSO itself, meaning the two modes are not completely independent. Okay. And so how do these modes of variability affect climate affect climate over North America? And here you can see a figure that shows the effects of ENSO and the PDO on the US. And you can see on the left precipitation and on the right temperature. And here a red color is a positive correlation and a blue color is negative. So basically, you can see that like a positive phase or an El Nino event would have a kind of positive impact where it's red. And you can see that the two modes have similar effects on North America, precipitation and temperature, although there are regions where there are differences. For example, if you look in this on the left in the central US, ENSO has a much stronger influence on precipitation in the middle of the continent than the PDO does. Whereas if you look at temperature on the right, you can see that the PDO has a much stronger effect on the coastline, the western coastline, than ENSO does. So there are local and regional differences. Okay. So previous studies have looked at the combination of ENSO and the PDO and their effect on North America. And this figure here shows one of the first studies to look at whether El Nino events that occur in different phases of the PDO have different impacts. And here you can see precipitation. And basically what this figure shows is the dark color means precipitation is larger than usual and light colors means it's less than usual. And this kind of early study showed that indeed El Nino events that occur in different phases of the PDO can have different impacts. Although these early studies are very limited in the fact that we have just such short observational records, so it's difficult to see whether these differences are truly statistically significantly different. More recent studies have revisited this question, and in this case, this study uses the IPO or the Interdecadal Pacific Oscillation, which is highly related to the PDO. And here they show temperature on the top and precipitation on the bottom. The left-hand panel shows El Ninos that occur during a positive phase of that Pacific decadal variability minus just El Ninos. And the right shows El Ninos minus El Ninos that occur in a negative phase of Pacific decadal variability. And basically what they show over North America is that the Pacific decadal variability can have an influence on ENSO temperature teleconnections in the top two panels, where you can see that effect kind of over Canada and North America. And it's a little bit harder to see with the precipitation, but there are effects, particularly along the coastline and in the southern US. Okay, but all of these previous studies have either used observations or single models. And there are some problems with this because the observational record is really short and we have very limited observations of different phases of the PDO. Using single models can be difficult to interpret because different models have different biases, and it's a little bit difficult to say how they can relate to the real world. And when we look at CMIP, which has lots of different models, they only often use one realization. And again, this is a really short record that doesn't necessarily characterize that decadal variability well. And so today what I'm going to do is revisit the question of whether ENSO teleconnections over North America are modulated by the PDO, and I'm going to use 5 smiles to do that. And so when I say modulation, what I mean is are El Nino teleconnections over North America different when they occur during different phases of the PDO, okay? So we're going to look at El Ninos during positive PDOs and El Ninos during negative PDOs and see whether they have the same or different impacts. And the advantages of using smiles for this is that there's just lots and lots of events, which is what I mentioned in the introduction. And so this means that we can actually statistically robustly compare those different ENSO events during different phases of the PDO. So when we look at composites of events, we can say whether they're truly different or not, because we know that we've really sampled the range of, sampled the variability basically. And today I'm going to use 5 smiles to check the robustness across different climate models. Okay, so before we delve into the scientific question, we first need to ask, well, can the models actually represent the processes and the teleconnections that we're interested in? Are the models fit for purpose? And to do that, what we're going to do is we're going to do some comparison of the models with observations. And here I'm showing ENSO teleconnections in observations for temperature in red and blue and precipitation in green and brown. And the top left is always observations. And then for each of the climate model, or each of the 5 smiles, I'm showing you the ensemble member that has the highest correlation with the observed temperature teleconnections. Okay, and so if you look at the red and the blue, or the temperature teleconnections, you can see that in general, the overall pattern over North America is well represented in all the models, but you can see that there are local or regional differences. When we look at the pattern correlation between observations and each of the models, you can see that it's quite high, with the lowest correlation being 0.7 and the highest 0.85. And you can see that the MPI model and the GFDL SpearMed model do particularly well in this case. When you look at the bottom for precipitation, which is the same member as shown in the top panels, you can see again the overall pattern of teleconnections is well represented, but there are local differences, particularly over the western coastline. Okay, so we can do this again, and now we can look at the highest correlated member for precipitation. And you can see that that does improve the representation of precipitation in the model, which you might expect. You can see again, the correlations are pretty high, and that the CSM large ensemble, CSM1, this is, MPI and GFDL SpearMed all do really well, but the other two do pretty well as well. And you can see if you look in the bottom panels for temperature that again, the broad scale patterns are well represented, but there are local differences. So what does this tell us? It tells us that in general, we can represent what we observe in the models, but that there are kind of local regional differences. So we want to be a little bit careful about using this at kind of those really small scales. We also want to know whether the models can represent the PDO correctly. And here I show basically a very similar figure comparing observations with the models. And we find that indeed that horseshoe pattern of the PDO can be found in all of the models. The correlations are again really high for all of the models, and highest for CSM and GFDL SpearMed. And you can see kind of some known biases. We can see the kind of the tropical Pacific bias that's found for ENSO occurs in the decadal mode as well, where it's kind of shifted to the west. We see some cold bias in some of the models over the Kuroshio region. But when we look off the coast of North America, it looks pretty good. So we can really represent the PDO in all of these models. And so now that I've determined that the models are pretty good and fit for purpose, we're going to go back to that scientific question and look at the modulation of teleconnections by the PDO. Okay, so what I'm going to do is I'm going to composite events or El Nino events in different phases of the PDO. And here I'm showing the results for CSM1 large ensemble. So this first panel shows El Nino temperature teleconnections over North America when the PDO is positive. We can then add El Nino temperature teleconnections when the PDO is negative. And I'll note here that the stippling shows when it's not statistically significantly different. So those two panels are significantly different when there's no stippling. And you can see here that we have warmer temperature teleconnections over Canada and Alaska when the PDO is positive as compared to when it's negative. We can do the same thing for precipitation. And here you'll see that the largest differences are found in this kind of blob off the California coastline that extends onto the coastline. And that blob and precipitation is larger when the PDO is positive compared to when it's negative. Okay. But I told you I was going to look at multiple models and see if these results are robust across them. So we can extend this plot to look at 5 smiles. And that top row is exactly what I just showed you. And now if you extend down the, all the rows, you can see all of the different models that I'm looking at. And you can see surprisingly consistent results. We find this warmer temperature teleconnection over Alaska and Canada when the PDO is positive compared to when it's negative for El Niños in all models. And while the blob off of California for precipitation, the magnitude of that blob is kind of model dependent, the modulation of it by the PDO exists in all models. And so we're really finding these consistent results that show that temperature teleconnections for El Nino are different over Alaska and Canada between different phases of the PDO, and precipitation teleconnections are different off the coast and onto the coastline of California. Okay, so what's going on here? We can because we have smiles, what we can now do is try and separate out the effects of El Nino and the PDO in the absence of each other. And so what we're going to do here is we're going to look at El Ninos that occur when the PDO is neutral, and we're going to look at PDO events that occur when ENSO is neutral and see how they combine to give this effect. And so here you can see an El Nino when the PDO is neutral. We can then look at PDO positive when ENSO is neutral, and you can see that the teleconnections are kind of similar, but they have regional differences, and the PDO tends to have weaker teleconnections than ENSO. We can then add those two panels together, and then we can see what happens when we look at El Ninos that occur when the PDO is positive. And what we actually find is that we get a very similar result by just adding the two modes in the absence of each other and looking at the two modes when they co-occur. So what we're really finding is kind of a linear combination of the effects of the two in the absence of each other. And again, we can extend that to all 5 smiles, and we find a very consistent result across all of the models. And I'll note that I'm not going to show this today, but it's fairly consistent for looking at the negative phases of the PDO and La Nina. Okay, so what's going on here? What's driving these differences in teleconnections between different phases of the PDO? Sorry, I'll just note that that's also true for precipitation teleconnections. Yeah. Okay, so what's kind of driving this? To look at the drivers of what causes the teleconnections to be, the ENSO teleconnections to be different in different phases of the PDO, we're going to go and look at GFDL SPEAR MED in more detail. And I'm going to do that for 2 reasons, or 3 reasons actually. First, because if I show you all of the models, it's just going to be a giant mess of panels. Second, because GFDL SPEAR MED consistently had those highest correlations when we were looking at whether the models are fit for purpose. And third, because this model has a really high atmospheric resolution and land surface resolution, which means it has been suggested to better represent kind of the hydroclimate. And so this seems like a good model to really look at the teleconnections, particularly for precipitation over land. Okay. So we can start again by looking at the similar plots that I showed before. And here I show El Nino teleconnections when the PDO is neutral for temperature. And I'll note in the top, in the titles, I have the number of events that we're compositing. We can then add El Ninos when the PDO is positive, El Ninos when the PDO is negative, and on the far right, that difference between El Ninos in a positive PDO is El Ninos in a negative PDO. Okay. We can add precipitation, and you can see for temperature and precipitation the results that I mentioned before. But what's driving this? We're going to look into the atmospheric circulation differences to see kind of what's going on here. So now we're going to add sea level pressure. On the left, we have the typical El Nino sea level pressure anomalies when the PDO is neutral. And here I'll note the black contours are kind of the mean state. So you can see how the El Nino anomalies relate to the mean state. And you can see in pink this negative sea level pressure anomaly, which is basically the Aleutian low. If we move over to the next panel, and here the gray dash contours are just the left panel to kind of see the differences when the PDO is positive and when it's negative. You can see that when the PDO is positive, the Aleutian low is further deepened, enhancing those teleconnections. And when it's negative, it's weakened, weakening those teleconnections. And so basically what we find is the Aleutian low is deepened when the PDO is positive, which brings more warm air to Canada and Alaska and enhances those temperature teleconnections. There's also a higher pressure over the North American continent, and this has been suggested to cause less cold air outbreaks and also enhance those temperatures. The other thing we can look at is the Pacific jet, which is shown by the zonal mean, zonal wind. And here again, you can see the same thing on the bottom panels, but here we have a latitude versus pressure coordinate. Again, those black contours on the left are the mean state. And you can see for the bottom left, what we know happens for an El Nino, that the Pacific jet is strengthened and moves south. That's those red anomalies. And again, we can see that when the PDO is positive, these El Nino anomalies are enhanced, causing an enhancement of the storm tracks, which brings more precipitation onto the California coastline. And when the PDO is negative, the teleconnections are weakened.
Nicola, we had a clarification question.
Oh, sorry. Yep.
Oh, yeah, no worries. Could you please define what positive, neutral, and negative mean for ENSO and PDO?
Okay, yeah. So in this case, I'm looking at kind of El Nino is defined as a Nino 3.4 index. And the PDO is defined using the climate variability and diagnostics package. And basically positive is when the time series goes above 0.5, and negatives when it goes below 0.5, and neutral's anything in between the plus minus 0.5 range. Does that make sense? Yeah, okay. And that's kind of the standard way of defining the PDO. It uses an EOF. Okay, yeah. And so the results I've shown you here are for the winter season, so DJF. But we can also look at the same thing for spring, or March, April, May. And you'll see here, I won't go into too many details, but we find basically the same effect, but it's weakened. So basically we're finding this result persists into spring, but it's kind of smaller. Although I will note that we find more that the precipitation anomalies that are significant extend further onto the coastline in spring than they did in winter. Okay. All right, so what does this mean exactly? And the really cool thing we can do, because we're using large ensembles in this case, is we can look at now, instead of composites of events, we can look at the whole distribution of events, and we can create these probability distribution functions shown in this plot here. And on the left, I show surface temperature. On the right, I show precipitation, and we're showing two different regions for each. So how do we kind of interpret this? If you look at the top left, we have Alaska. And here you can see neutral. So that's El Nino neutral, PDO neutral. So that in between the 0.5 range I just mentioned is shown in blue. And you can see this kind of distribution that's centered on 0, where you can have positive or negative temperature anomalies over Alaska due to climate variability. You can see how that distribution is shifted due to ENSO and the PDO. So if we look at El Ninos in yellow, you can see that that distribution is shifted to the right. And we have a higher likelihood of having warmer temperatures over Alaska when there's an El Nino. You can see that that yellow distribution is shifted again further to the right in the red when the PDO is positive, and shifted kind of back towards the left when the PDO is negative, showing that enhancement and diminishment of El Nino by the PDO that I was talking about before. And I'll note that you can see that this is important for kind of extremes, those warmer temperature, extreme summers, winters. DJF always gets me because I'm Australian. Those winters occur more often when you have an El Nino in a positive PDO. But you can also see that this isn't predictable. These two phases don't tell us exactly what's going to happen, because if you look at that red PDF, you can still have negative anomalies over Alaska when El Ninos occur in a positive PDO, just because there's so much variability. If we look at the bottom left, and this is a region offshore of the western US coastline, so this is basically where marine heat waves occur, you can see again that El Nino and the PDO are important for shifting the distribution. But as before, they're not, they don't tell us everything, and you could still have negative anomalies, although you're shifting your distribution so that you're more likely to have those warmer anomalies during an El Nino that occurs in a positive PDO. On the right, I'm showing two regions. On the top, the Rio Colorado River Basin for precipitation, and the bottom, San Diego, California. And you can see in this case, the colored lines are the red, yellow, and green compared to the blue, show that El Ninos shift the distribution. And you can really see that over San Diego in the bottom right, where the distribution is really shifted by an El Nino compared to a neutral year. But in this case, we don't find significant differences between different phases of the PDO, meaning that in the winter season, the PDO isn't really having a large impact on El Niños in these regions. However, we can show exactly the same plots for spring or March, April, May. And I'll just focus on the right-hand plots here again for precipitation. And you can see that in spring, actually, the distributions are significantly different in different phases of the PDO. And so in that case, what we can really say is that for precipitation over the Rio Colorado River Basin and San Diego, the PDO doesn't really have a large effect on El Nino events during the winter season, but it does during spring. And that's kind of what I was showing in the maps before when I said the precipitation seems to extend up more onto the coastline in that March, April, May spring season. Okay. So I'm going to put up a whole bunch of post-its here, and I'm going to go through this, so don't worry. But the last thing that we would be interested in is talking about whether these teleconnections change in the future. And we're going to here show the difference between 2050 to 2099 compared to 1950 to 1999 for all the models again, because we know that models differ in their future projections. So we want to see if the models agree. And here I show again temperature on the left, precipitation on the right. And I show the difference for El Niños, the PDO positive, and then El Niños that occur when the PDO is positive. And what I want you to note here is that most of the map for all of the projections is covered in stippling, which means it's not statistically significant. We do see individual models that have statistically significant differences in small regions, but there is not really agreement across the models. And when you think back to those PDFs I just showed you with the huge variability, you can see we have small changes that aren't statistically significant, that don't agree across models, and we have these huge PDFs of variability. And so basically what I think this really tells us is that we're unlikely to observe a change in these teleconnections in the next 50 to 100 years. Okay, so to conclude the first part of this talk, what have we found? We found that the PDO modulates ENSO teleconnections over North America. And basically what's happening is the PDO positive is amplifying El Nino and diminishing La Nina, with the PDO negative having the opposite effect. I didn't go into this in the talk, but it's actually more likely to amplify than diminish because you have more occurrences of El Nino in a positive PDO than a negative PDO. And this comes back to the fact that the two modes are not completely independent. We find the largest effects are over Canada and Alaska for temperature, and that California coastline for precipitation, and that this effect persists into spring where it's smaller but can be more important for precipitation. And this is driven by kind of a modulation of the Aleutian low and the Pacific jet. We find that this effect is a linear combination of the two modes when you composite them in the absence of the other. And when you think about the PDFs I showed you, you can see that this can be really important for the likelihood of kind of those extreme temperatures and precipitation anomalies, but the two modes can't be used to predict temperatures because there's so much variability, meaning that while you're more likely to have a warm Alaska, for example, when the two modes are positive, you could still have cold anomalies just due to that high variability. And I've suggested that it's unlikely that we observe future changes. Okay, so I'm going to leave the teleconnections there and I'm going to move on to the second part of the talk and look at ENSO itself. Okay, so we're going to now try and answer the question of whether ENSO itself will change in the future. And now I'm going to extend out the smiles and we're going to use 14 different smiles to look at this question. Okay, but before we do, let's go into a little bit of background of ENSO and how our understanding of how it might change in the future has kind of evolved from CMIP 3 to CMIP 6. So this figure here comes from CMIP 3, and it shows a change in both ENSO, so that's the y-axis, the ratio of El Nino-like variability. So kind of ENSO variability increases if it's above that one line and decreases if it's below. And the mean state pattern, which is the x-axis, and you can see the El Nino-like or the La Nina-like change. And here you can see that in CMIP 3, we think it's most models show an El Nino-like background warming, but some models don't. And more models show an increase in ENSO variability than a decrease. But again, not all models show that. So how has our understanding kind of evolved in moving to CMIP6? So this recent figure comes from CMIP6. And the top panel shows the E-index variability, which is a way of characterizing Eastern Pacific El Niños. And the bottom shows the C-index variability, which is a way of characterizing those Central Pacific Niños. And the two time periods, so 200-year time periods, are shown in the blue and the orange. And basically the top panel showing that the orange panels are larger than the blue panels, saying that we're seeing an increase in ENSO variability for those Eastern Pacific Niños. And when you look at the Central Pacific in the bottom panels, you can see, again, most models show an increase, but not all of them. Okay. However, other studies that look at longer timescales find kind of an opposite response. So this figure before was showing us that we're more likely to see an increase in benzo variability in the coming century compared to the last century. But this figure here uses the long run MIP, so further out into the future. And what they actually find, if you look at, is a decrease in ENSO variability in most of the models. And so you can see the zero line shown in the black. And you can see that most models actually find if you extend out into the future, you see a decrease. So these two studies seem to be maybe a little bit at odds, or maybe we're looking at a timescale problem here. So we're seeing kind of in up to 2100, our models are suggesting that ENSO variability will increase, whereas longer out, it looks like ENSO variability will decrease. So how do we kind of investigate this further? You saw in the previous study that to really get at ENSO variability changes, the authors needed to use 100-year periods to estimate ENSO variability. And that's where the smiles come in. So here I show two figures from two different studies. The one on the left looks at Nino indices to get at ENSO amplitude, whereas the one on the right uses these E indexes on the top and C indexes on the bottom. So remember, this is the Eastern Pacific and the Central Pacific Ninos. The left-hand study, the black is CMIP and the red and the blue are large ensembles, whereas the right-hand study, the blue is CMIP and the pink and the red are large ensembles. But basically what both studies are showing is that a large part of the differences between CMIP models can be found by just using a large ensemble, because ENSO is so variable. If you look at a single model initial condition large ensemble, you have this huge range, if you look at individual members, of what ENSO might do in the future. And so this really, I guess, gives us a premise to use large ensembles to look at ENSO changes. Because previous studies are kind of limited by the use of single ensemble members, because they really can't look at the time dependence of ENSO changes. So this is going back to the compositing over 100-year periods. And it can be difficult to separate the forced response from internal variability. For example, if CMIP models are doing different things, is it because ENSO is really variable, or is it because they're really doing different things? And so to really get at that, we're going to use 14 smiles to revisit ENSO projections. Okay, so here we go. Here are our 14 smiles, and the bottom right is observations. Here we're looking at ENSO variability. So this is the standard deviation of Nino indices over 30-year periods. Each panel is a different large ensemble. Nino 3 is in blue, Nino 4 is in red, and Nino 3.4 is in green. And you'll see 3 lines for each, with the middle line being the ensemble mean and the 2 outside lines showing the ensemble spread. And for the large ensembles, you can also see dots, and that gives an estimate of observation at different time periods to kind of see how that relates to the large ensembles. Okay, and so there's a lot going on here, but there's some really interesting behavior. First, you can see that the models over time are not doing the same thing with the Nino indices. But you can also see that for a lot of models, there is a time dependence that we really miss by kind of using 50 or 100-year periods to look at ENSO variance. So I'll point out a few. can you see my cursor? Maybe Dan can nod if you can see it. Yeah, cool, great. So for example, on the top right, if we look at this GFDL ESM2M model, you can see that ENSO variance increases and then decreases over time, showing this time dependence behavior. And this is really interesting because this model has been used a lot to talk about how ENSO might decrease in variability in the future. But you can see that that story, there's a bigger story here where there's an increase and then a decrease. Another interesting model that does something similar is CSM2 over here, where you can see again an increase and then a decrease. And actually, if you looked at kind of the beginning and the end here, you might conclude that the model doesn't see a change in ENSO. But again, you'd be kind of missing something by doing that. And then there are, of course, other models with interesting behavior. CAN-ESM2 shows this kind of decrease over here. Whereas other models like the IPSL one here show kind of a linear increase. So there's a lot going on here in the different models. Okay. And so we could stare at this for hours, but we're going to move on and look a little bit at the patterns. And for the rest of the results, I'm going to show you two time periods. I'm going to show you 2021 to 2050 compared to 1950 to 1980, and the end of the century compared to that earlier time period, as you've seen that there's some kind of time-dependent response going on in a lot of the models. And so here we're looking at the patterns of ENSO. So basically what's been done is that ENSO's been filtered, the SST has been filtered on a 2 to 7 year frequency. And you can see the change in the pattern in the tropical Pacific. And this is really interesting again, because you can see that the pattern is changing, but it's changing differently in different models. So you can, for example, we can pick out some models. We can look at GFDL ESM2M again over here, and you can see this kind of decrease in variance across the tropical Pacific. If we look at, say, MEROC 6 over here, you can see an increase across the whole tropical Pacific. Whereas if you look at the other MEROC model over here, it's kind of concentrated in the Eastern Pacific. So we really see a range of responses across the different models. And interestingly, if you look in the bottom right at the multimodal mean, you can see something that has been discussed in the past, which is kind of an increase in ENSO variance and perhaps a large increase in the Central Pacific. But you can see that by using the multimodal mean in this case, you're really missing a lot of the behavior that's going on in the individual models. And so we can look at the later time period. And again, I'll point you to an interesting case first, which is CSM2 on the top right. Okay, if you have a look at that, now we're going to change the slide. And you can see that when we look at the later time period, that CSM2 difference looks significantly different. We were seeing an increase in ENSO variability across the tropical Pacific in the earlier period, and now you can see that decrease. And you can see if we look at this later time period, the colors become larger, so we're seeing larger differences. But the multimodal mean on the bottom right looks kind of similar. And you can see again, there's kind of these different patterns if we look at different models. Okay. So we can look at this in a different way. And here we're looking at a Hofmöller of El Nino events. And I'll just go through exactly what this figure means first. So again, we have all of the different models. The contours show an El Nino composited across the time period, composited across 1950 to 1980. And the colors show the difference between the 2021 to 2050 period and this original period. Here you can see the x-axis is latitude, so you're seeing the tropical Pacific, and here time is moving up. So earlier is down here and time is going in this direction. And so basically the colors are showing us how El Nino events look different. And in this case, El Ninos actually, we're using a 0.75 anomaly instead of a 0.5 for the Nino index to get these El Ninos out in this case. Okay, and so there's a lot going on here as well. But here we can start to see kind of both the time and the longitudinal differences in the future compared to the past of El Nino events. And so, for example, if we look at something like this GFDL CM3 model that I'm highlighting in the middle, you can see that increase in El Nino variability that kind of occurs at the same time as the original peak, so those black contours. But if we look at different models, we see a different effect. You can see this EC Earth model here. The kind of increase in ENSO anomalies are occurring after the original ENSO peak. So maybe these ENSOs are persisting longer. If you look at MIROC 6 down here, you can see that that increase is kind of offset and occurs more in the Central Pacific. And so that's kind of, this is another interesting way to look at how the models are behaving and how they look different. And again, I'll point you to CSM2 on the top right, and you can see the pattern. You can see that basically what we're seeing is an increase in ENSO. And if we move to the later period, you can see that that looks a little bit different. But in general, in the later period, we're seeing larger differences, but they're large. In some models, they're largely the same, and in others, like CSM2 on the top right, it looks somewhat different. Okay. So there's a lot going on here, but we're going to move on to look at one last thing, which is the mean state change, which we talked about before in the introduction to this topic. And I'm going to look at the mean state change because it's been suggested to be related to ENSO changes. And here, when I talk about the mean state, we're going to look at an east-west gradient difference. But this is basically whether we're looking at whether the tropical Pacific warms, kind of everywhere warms the same, whether it warms in an El Nino-like fashion, so the Eastern Pacific warms more than the Western Pacific, or whether it warms in a La Nina-like fashion where the Western Pacific warms more than the Eastern Pacific. And you can see here time series for each model and for each month. And basically red means El Nino-like warming, blue means La Nina-like warming, and white means everything's kind of warming at the same rate because we're looking at an east-west difference. And again, you can see model differences. If you look at the bottom right multi-model mean, you see what we see in the CMIP mean, which is El Nino-like warming across the models. But if you look at individual models, you can see some differences. We can see that CSIRO up here has La Nina-like warming. Some models have El Nino-like warming in all seasons, but other models, such as this GFDL model here, has El Nino-like warming in some seasons, but La Nina-like warming in other seasons, with the other GFDL model over here actually showing the opposite. So again, you can see that there is something going on here, and by teasing out the different seasons, we can see that not only do the models not necessarily all show the same thing, they might show different things in different seasons that might be kind of averaged out if we just look at an annual mean. Okay, so that brings me to my last plot of the day, which is hopefully going to sum up some of what we've found here and is slightly complicated. So let me go through it slowly. Here, there are 4 panels. There are only 4 panels for visualization purposes because if you put them all on top of each other, you don't see anything. Again, we're showing all of those 14 smiles. And in this case, the colors are time. So blue is the beginning of the time series and yellow is the end of the time series. And for the first point of the time series and the last point of the time series, you can see these little colored dots that just give you an estimate of the ensemble spread. Here on the y-axis, we have the change in ENSO variance, or the ENSO variance itself, sorry. And on the x-axis, we have the mean state gradient. And we're going to look at the evolution over time. And so here in my cursor, I'm highlighting CSM2 again. And this has interesting behavior. So you can see in the blue at the beginning, we have our ENSO variance. And as we follow in time, you can see ENSO variance increases. And then we have this El Nino-like warming, and we have more El Nino-like warming, and ENSO variance starts to decrease. And this is really interesting because we see this behavior in a lot of the models. So you can see it in CSM1. You can believe that maybe if we had an earlier time series, you can see it in CAN-ESM here too. We see it in all of the models on the bottom left, where we really see this interesting time-dependent behavior that starts to kind of bring together a lot of what we're seeing, and maybe see that a lot of the models over time are doing the same type of response, but at different times. Okay, so let me sum up. What have we found by looking at ENSO in 14 smiles? Well, projections of ENSO variability are time dependent, which is why we're using the smiles and why it's really important to have large ensembles to look at ENSO. And we do find really large differences between different models when we look at the pattern and the evolution and the El Nino events. The mean state warming is El Nino-like in most models, but not in all models. And which season that occurs in isn't necessarily consistent across all the models. What we do find, however, is that many models show this time-dependent pattern where we should see an increase in ENSO variability concurrent with a small decrease in the mean state gradient, so an El Nino-like warming, then a larger El Nino-like warming and some kind of plateau or decrease in ENSO variability. And this is perhaps consistent with those studies I showed you at the beginning, where we saw an increase in ENSO variability in the next century, so that transient response, and longer term, a decrease in ENSO variability. And perhaps kind of this time-dependent response is really consistent and brings together some of those previous literature that maybe are not as different to each other as maybe they originally seemed. Okay, so to summarize, I first looked at ENSO teleconnections over North America and found that the PDO does modulate ENSO teleconnections, that it's more likely to enhance than diminish them, and this tended to be caused by changes in the Aleutian Low and the Pacific jet stream. When looking at ENSO projections itself, there was a strong time dependence and definitely differences between the models, but perhaps this kind of interesting behavior where ENSO increases, the mean state shows an El Nino-like warming, and then ENSO variability tends to decrease. That may bring together some of the previous literature. And I'd like to conclude by saying that smiles are a really valuable tool for investigating climate, coming back to where I started. And I hope that I've shown you today that by having so many events in question one, such as the ENSO-PDO combination, and by sampling variability, such as ENSO in the second question, that we've really kind of utilized the value of the smiles, and hopefully many other people will want to use smiles and utilize their value as well. Thanks.
Excellent. Thanks a lot, Nicola, for sharing your work. We now have some time for questions, so please feel free to raise your hands in the participants section, or go ahead and enter a question in the chat. So I see we have a couple. I think Judith, you had your hand raised first, so go ahead.
Hello. Hi, Nicola. Sorry for not switching my camera on. That was a great talk, really interesting. We looked at both ENSO and PDO ourselves. And my question is about the PDO. There's a paper by Ka-Kit Tung, which I found really convincing personally, about the PDO not really being a mode of variability, but a statistical artifact. I myself computed PDO indices, and it was the most sensitive index I've ever seen to averaging timescales, etc. So my question is, do you think that the PDO is a real climate mode that has some meaning beyond what pops out from a statistical analysis? Thank you.
Yeah, I'm not really sure I have an answer to that. It's kind of clear from previous studies that ENSO and the PDO aren't statistically independent, and I don't think it's really clear whether the PDO is a mode in itself or not. I do think that the index itself can be really useful to try and understand kind of teleconnections and what's happening over land, and maybe help to give us some predictability, which is why we're looking at it. But yeah, I don't know that I really have the answer to what the PDO is at this point. So I hope that kind of answers your question.
Thanks.
Great, thank you. Ayla, you had your hand raised next.
Yeah, I was interested in the mean state changes that you showed. And I guess there's this whole debate about whether all models are wrong and given the warming, like kind of El Nino-like warming. And I wasn't aware that really any models gave a cooling, but then you showed the or relative cooling of the East Pacific, but you showed that the CSIRO model does. And I'm wondering, has anyone looked into why that model does that? And do we think it's realistic?
Yeah, so that's kind of, in this case, we've taken all models at face value to see what they do. I think in the tropical Pacific, the CSIRO model has some pretty serious biases, so I'm not 100% convinced. Particularly, it's kind of hard to say because its ENSO is way too far in the Western Pacific, but whether that kind of whether that's going to change the mean state projections is a little bit unclear to me. I will note that if you look seasonally, it's not the only model that does have that La Nina-like warming, and it's still warming, right? It's just relative warming in the East versus the West. And I don't know of anybody that's looked further into the CSIRO model. I know that there are papers that have looked at the GFDL ESM2M model that has some of that behavior and argue that it's, there's no reason to believe that there's any reason it's less realistic than the other models.
Okay.
Yeah. So I think kind of the jury's a little bit out on that. Most of the models show El Nino-like warming, but the ones that show La Nina-like warming aren't necessarily wrong. And at this point, I haven't seen a good argument to say why we should discount one over the other.
Okay, thank you.
All right, Clara, go ahead.
Hi, Nicola, really nice talk. Thank you so much. I had a question kind of related to Judith's, and which is, how do you view the PDO related teleconnection? I and Isla and Karen McKinnon and others had done a paper where we looked at ENSO composites and teleconnections, and then just separated them by the strength of the Aleutian low, and found, of course, that, you know, it's very sensitive to that because it's just atmospheric noise that is causing that sensitivity. So I'm wondering, you know, are you thinking that the PDO is SSTs in the North Pacific really affecting the atmosphere? Or are you just picking up atmospheric noise with your SST PDO index? Have you thought about that? I think it's a really important thing, actually, issue.
Mm-hmm. Yeah. I think you're right. I think it could be, I mean, we could be picking up the SSTs could be related to the Aleutian low, and we could be picking that up, or the Aleutian low could be related to the SSTs. And then we're finding it in, I guess it could be going in either direction. So it could be a good idea to try and figure out what drives what, or maybe they're so interrelated you kind of can't do that. If you, I guess if you have any suggestions.
Yeah, I can
discuss later. Yeah.
Yeah, I'll follow up
really
with you. Yeah, we used an atmosphere only control run and showed that the variability of the Aleutian low was, you know, the uncertainty on the ENSO composites was really coming from atmospheric noise. So I have some ideas for how you might test that null hypothesis in your study. But thank you so much. It was a great talk.
Great. That'd be great. Let's follow up. I'd be interested to test that.
All right, Dylan, you're next.
Thanks. Awesome talk, Nicola. I appreciate you showing these results for everybody. I just wanted to ask a question and see how your results might align with another paper that sort of focused on the ENSO future ENSO variability question, and they also showed that ENSO decreases in their model, but in particular, they're using a model that has high horizontal resolution in the ocean. And they sort of make some arguments that you need, or they make an argument that CMIP models that are at coarser resolution get an increased ENSO variance because they can't capture the mesoscale ocean features that are important for some of these changes in different feedbacks. So I'm just wondering if you're using all these smiles that have relatively coarse resolution, are some of these smiles that are giving a decreased ENSO in the future, maybe are they getting that answer for different reasons? Or I guess I'm just trying to reconcile the results of this paper that has high resolution mesoscale ocean variability and getting sort of a similar answer, but you're showing a similar answer with coarser resolution models. So I'm wondering if all these models are getting the same answer, but for very different reasons, and what that could mean. And I can link this paper in the chat, by the way. It's by Christian Wengel and friends. So I think it's part of the Axel Zimmerman group in South Korea.
Yeah, so I've seen this paper. It's really interesting, and I don't have an answer at this point. I have absolutely no idea why the models are doing different things. And our kind of idea as a group to look at all of these ENSO metrics in 14 smiles is to kind of hopefully spark more research on it using these smiles that dig into individual questions in more detail and look at why we see what we see, because every single plot on ENSO with those 14 smiles I've shown here could be an individual study that goes into detail and looks at why each model is doing what they're doing and what's happening. And at this point, I think that'd be super interesting, but we haven't done it and we don't have a good answer yet.
Thank you. Appreciate it.
All right, Jerry, go ahead.
Hi, Nicola. That was really interesting. That's a lot of results to try to make sense of. I was just curious, when you showed those Hofmullers of the El Nino evolutions for all the different smiles, there was really a striking variety of the ways the models simulated composite El Nino events. And I was wondering, and of course, the composite El Nino event, you're already taking out some of the variety of Eastern Pacific, Western Pacific El Ninos and everything else, but say you just used a composite El Nino evolution from observations and tried to stratify your models based on how well they simulated that composite typical El Nino evolution. Would that be one way to kind of narrow in on maybe some of the processes that are producing some of these time evolving changes? Or what do you think about that?
Yeah, I think that's a great idea. So I think there's a whole bunch of things that could be done, and the kind of obvious first step is to say, okay, how do they compare to observations in general? And you can see with the Nino indices in the first plot, I showed that we did a tiny bit of that, but definitely looking at kind of the composite would be a good one to do, but also trying to understand other processes, like which models do what and for what reasons. But then again, this becomes a little bit of a rabbit hole for 14 large ensembles, and then looking at SST patterns and how well it represents that is a good start. But then there's mechanisms, and then is it getting the right pattern for the right reasons, as Dylan mentioned. So yeah, I think that'd be a good start, and I definitely do want to go kind of further down the what, when, why rabbit hole.
All right, thanks.
Excellent. Well, I think that about wraps it up. So thanks once again to Nicola and to everyone for the great questions. And I look forward to seeing you all next week.